And our last circuit theorem is the theorem for the maximum power transfer. In electrical engineering, many circuits require the maximum power to be transferred from a source to a load. And this source will have its own equivalent resistance as well. And here there arises two different problems. The first one is the problem of efficiency. Power utility systems are designed to transport the power to the load with the greatest efficiency by reducing the losses in power lines. In other words, we need to reduce RT, which represents the resistance of the source and the power line. Hopefully, one day when we will have room temperature superconductivity, this problem will be fully solved. The second problem is the effectiveness. In signal transmission, the problem is to attain the maximum signal strength at load. So therefore, we need to find a condition where maximum power is transferred to the load RL. In maximum power transfer problem, we want to find resistor value RL, which maximizes the power transferred to it. Power is defined as P is equal to I squared times RL. And we can write I simply as Vs divided by RT plus RL. Accordingly, if we use Vs over RT over RL instead of I in this power equation, we end up with the expression shown here. Vs over RT plus RL squared times RL. So now we have the power expressed in terms of the load resistance. In order to find the maximum power transfer point, we need to take the derivative of power with respect to the load resistor and equate this to 0. If we take this derivative using this rule from the calculus, we end up with this term. Vs squared times RT plus RL squared minus 2 in parentheses RT plus RL times RL divided by RT plus RL to the fourth power. The derivative will be 0 if this upper term will be equal to 0. And the solution of this quadratic equation gives us RT is equal to RL as the condition where this is true. So in other words, the value of the load resistor should be equal to the value of the source resistor, and then we will have the maximum power transfer. If we plot this using MATLAB or any other software, in which in the x-axis we use the RL over RT and in the y-axis we use P over Pmax, we end up with this plot. Here the Pmax P value reaches the Pmax value when RL is over RT is equal to 1. Find the load resistance RL that will result in maximum power delivered to the load for the circuit and determine the maximum power transferred to RL. So in order to solve this question, we need to find the Thevenin equivalent of the left side of the circuit. Let's do that. So we can start with the V open circuit, plus minus 180 volts. I have my 30 ohm resistor. Here I have the V open circuit. And here I have the 150 ohm resistor. So due to the voltage divider, I calculate V open circuit as 150 divided by 30 plus 150 times 180 volts, and accordingly V open circuit is equal to 150 volts. As the second step, I will find the Thevenin resistance by short circuiting the voltage source, and I end up with 30 ohms in parallel with 150 ohms, and here I have the open output ports. So our equivalent, our Thevenin, will be 30 ohms in parallel with 150 ohms, and this will be equal to 1 over 30 plus 1 over 150, which will be equal to 4500 divided by 180, and this will be equal to 25 ohms. So our Thevenin is 25 ohms. Accordingly, the equivalent circuit becomes the open circuit voltage of 150 volts and the Thevenin resistance of 25 ohms. And for the maximum power transfer, our load should be equal to the 25 ohms. And in this case, the power transferred will be P max, will be equal to the current passing through this circuit, 150 volts divided by 50 ohms squared times 25 ohms, I squared times R. So here I have 225 watts. This will be the maximum power transfer to this load for this circuit. I need to find the load resistance RL that will result in the maximum power transfer delivered to the load for this circuit. So in other words, I need to find V open circuit and I short circuit, assuming that RL is not there. I think the easier one is the I short circuit, because if I short circuit this element, then this 4 ohm resistor will be bypassed. If I will have here the reference node, I will have here 0 volts and here 0 volts as well. And VAB will be equal to 0 volts too. And then I can just have the 2 VAB is equal to 0 as well. And the whole circuit reduces itself to this very trivial circuit. 6 volts, 6 ohms, and I short circuit is passing through here. Accordingly, I short circuit is 6 volts over 6 ohms, which is 1 amperes. I found this. Alright, in the previous slide, we found I short circuit is 1 amperes. Now I need to find the V open circuit. V open circuit will be equal to VAB, and therefore 2 VAB here for this dependent voltage source will be equal to 2 times V open circuit. Let's write the Kirchhoff's voltage law for this circuit, assuming a current I is flowing through that. 6 times I minus 2V open circuit plus 4 times I is equal to 6. Now I can write this in a simpler form as 5 times I minus V open circuit is equal to 3. Now, can I write a relation for V open circuit? Yes. Assuming that this node voltage is V open circuit, here I have the reference node, I can write I is equal to V open circuit divided by 4. Wherever I see I can plug in this new expression, and therefore this becomes 5 over 4 times V open circuit minus V open circuit is equal to 3. If I solve this, I end up with V open circuit is equal to 12 volts. Now, if I have V open circuit is equal to 12 volts and I short circuit is equal to 1 amperes, our Thevenin will be equal to V open circuit divided by I short circuit, and accordingly 12 volts divided by 1 amperes is 12 ohms. The load resistance RL should be equal to the Thevenin resistance of the circuit, and therefore the value of that will be also 12 ohms for maximum power transfer.